Okay, let's break this down. I said if males compete for space, so I'm giving you information. I'm saying, like, let's assume they compete for space. A large male will likely force a small male. Well, it seems reasonable that size is an important determinant of dominance here. So I think that sounds good. To spend less time on the side with the optimal temperature. Now, if you're the large male and you're dominant, you're going to want to be where the optimal temperature is. And are you going to want that other male in there trying to fertilize the eggs of your female? Absolutely not. So I think that this reads as a true statement, that if we can assume males compete for space, that large males will try to force small males out of space that they desire. Keep them out of their territory. Will you see this in the experiment, however? That's the question. Well, up at the top here, I'm showing exactly what you've already seen. These are the data that you just wrote a figure legend for. But now, if we repeat the experiment, as Magnuson and his students did, if we repeat that experiment with 2 bluegills in there, and now the other bluegill, the second one, is a larger bluegill, look what happens. When you put a bluegill in there with a larger adult bluegill, what happens is instead of now being at 31, like it was here and here in these 2 trials, it's now never at 31. It spends all of its time at 27 or 34. And we know from the first experiment that that's not what it prefers. It prefers not to be at those temperatures very much at all. But it's going to spend all of its time there because that larger bluegill is, excuse my French, kicking its ass. Now, I don't want to always blame the poor French when we curse, but you know what I mean. The idea is that there's a dominance interaction here that prevents the small bluegill from being where it wants. So if we take that back to the field, it tells us something about what happens in nature. Organisms compete for limited resources. In this case, the limited resource is that thermal resource, or space at a certain temperature. And there's only going to be so many places in that lake where you can have a territory for a bluegill to reproduce. When all those spaces are filled, you won't have any more male bluegills that get to reproduce. And so we can imagine now that that's going to limit the size of the population of bluegills in that lake. And this becomes an important thing to think about when we consider the population growth model that we've been working with. It's a model where the rates of birth and the rates of death remain the same for an individual, regardless of how big the population is. But that's not very realistic, is it? In this case, we've seen that as resources start to dwindle, as you run out of space or food or water or any other resource that's necessary, what will happen is some individuals won't get to reproduce. So the average reproductive rates of individuals in the populations should go down. And what that means is the population won't grow as fast as it was in the past. How do we capture that in a mathematical model? Well, let's think about what we've assumed with our very simple model of exponential population growth. And that model is that the population grows at a rate of R per individual. And R is births minus deaths, to remind you. But what we're saying here now is that the birth and the death rate is going to change, which means R is going to change over time. And it changes specifically as the population size increases. And so instead of having this flat line, which you see here, where the rates of birth and death do not depend on the density or the number of individuals in the population, which is what density is, instead we might have something that looks like this. That line decreases, such that as the number of individuals in the population increases, as the density increases, that the births and the death rates are changing so that R goes down. Effectively, the birth rates are going down or the death rates are going up. Either way, that R is going down. And so now the population is growing slower and slower and slower until you get to a population size that's this large. And at that point, the population stops growing altogether because R is equal to 0. And 0 times any number of individuals is 0 population growth. And we call this point, this population limit, the carrying capacity, or K. And the reason why we give it a letter K is because if we're going to put it into a mathematical model, we need to make it a parameter that has a letter. So we keep track of it. And that population growth model looks something like this. You'll find this model in your textbook. And you'll also see it explained in more detail in a video that I've made that you can watch next. But for right now, I just want to point out the interesting features of it, that it shares in common part of it with this very simple model of exponential growth. What's new is this part of it here, which is k minus n divided by k, which basically is a factor. I'm going to clean this up a bit. It's a factor that allows you to adjust this rate of population growth by the number of individuals in the population. And as those individuals approach k, then this whole term goes to 0. And as this whole term goes to 0, population growth goes to 0. And that's the interesting feature of this model, and that we've taken a model that we developed already, a simple model, and we've relaxed an assumption about that model, which is that the births and deaths don't depend on density. We said now they do depend on density, and what happens if the population growth rate depends on density? Well, it depends on the population size. But at very low population sizes, where n is close to 0, you can see that this whole thing is going to be close to 1, which means that the population approximately grows like an exponential population, which means that at very low densities, we can kind of recapture that exponential growth. It's only once the population starts to grow that then it slows down and ultimately approaches a carrying capacity. All right, let's explore some other assumptions of these models, which we may or may not have made explicit in the past. Let's kind of bring them out and say, what are they? True or false? Both models assume that no individuals immigrate into the population. Remember, immigration is moving from outside the population into the population. So do you think this is true or do you think this is false?